Hi. In this program, we'll take a look at how to do calculations with measurements. In my example, what I'm going to do is look at two different ways of doing a calculation, one where the error is known and one where the error is not known. The calculation we're going to do is to determine both the volume and the density of a rubber stopper. The volume will be determined by placing the rubber stopper in a partially filled graduated cylinder and use the difference between the before and after to determine the volume. Then we'll use combinations of mass and volume to determine the density of the rubber stopper. As I mentioned, in the first method, we'll take a look at where the uncertainty, or delta x, is not known. In our second time through the problem, we'll take a look at how to do the calculation when the uncertainty is known. So let's begin with when the uncertainty is not known. First, I'm going to determine the volume by subtracting the before and after. Here we can see that calculation. Now, when you put this through your calculator, it'll probably just read 7. But should we write the answer as 7.0 or 7.00? Well, for that, let's turn to the rule. The answer should be quoted to the same number of decimal places as the least precise value. In this case, both of our volumes have 1 decimal place. As a result, my final answer should also have 1 decimal place. So I should change that from just 7 to 7.0. Now we'll determine the density of the rubber stopper. Density, as you can recall, is mass divided by volume. Here you see that calculation. You'll notice that I've not used the 7 milliliters, but rather the original data. In this case, I'll avoid any rounding off errors that may occur. So always go back and use your original data to determine any sort of complex calculation. Here my calculator spits out at the end 2.347. Now, at this point, how much should I round that answer off to? Here, because I'm doing an operation of division, or if it was multiplication, my final answer should be quoted to the same number of significant digits as my least significant value. For that, we take a look at the number of significant digits in our data. That first 21.5 has 3 digits, the volume 3 digits, and our mass 3 digits. So my least significant digit here would have 3. So at first glance, one might think I should round this off to 3 digits and change it to 2.35. But upon closer examination, when we determine the volume by subtracting those two values, which is the operation done in the brackets, that 7.0 has only 2 significant digits. So really, that number on the bottom has only 2 significant digits. As a result, my final answer should only have 2 significant digits. So it should become just 2.3. Now let's do the calculation where the uncertainties of our measurements are known. Again, we'll start by finding the volume of the rubber stopper by subtracting our 2 values. And again, the calculator will just read 7. Again, how many zeros do we put after that? The rule says that when we are dealing with uncertainties by addition or subtraction, we always add them together. So in this case, the uncertainty in my volume, I'm going to add together the uncertainties of both of the volume before and after. And I get 1.0 milliliters, or cubic centimeters. The general rule is to reduce our absolute error to 1 significant digit. So as a result, I would write that as plus or minus 1. Now we're going to bring our final answer and our uncertainty into what we call agreement. What I mean by that is, how many decimal places does our uncertainty have? Well, it has no decimal places. Our measurement, the 7, should therefore also have no decimal places. So we should write our final answer as 7 plus or minus 1 milliliter. Let's take a look now at calculating the density of the rubber stopper. Again, mass divided by volume, and I get the same answer as before, 2.347. Now, when dealing with multiplication or division, our rule is we have to add together the relative uncertainties or percentage uncertainties in each of our answers. So the uncertainty in the density, I have to add together the percentage uncertainty in the mass with the percentage uncertainty in the volume. Percentage uncertainty or relative uncertainty is obtained by dividing the uncertainty by the measurement itself. So we can see here that the mass, 0.01 divided by 16.43. Multiplying that by 100 gives me about 0.06% error in the mass measurement. When I'm determining the volume, as we saw before, I have 1 over 7. That constitutes about a 14% uncertainty. This analysis shows me that if I really wanted to improve this particular experiment's precision, I really need to take a look at another way of measuring the volume of this cylinder because it's such a massive contributor to the error. Anyway, at this point I know my final answer has a 14% uncertainty associated with it. So I'm going to take 14% of my final answer, and that will then convert it into an absolute error. So taking 14% of our 2.347, I get 0.03337. We round that off to one significant digit, as before, which is plus or minus 0.03. Now I have to bring my final answer into agreement with that. And since that 0.03 has one decimal place, so should my final answer. So I round that to 2.3. So there's a quick look at two different methods or two different ways of doing calculations with measurement, one with the error known and one with the error unknown. Remember, comments are always welcome, and thanks for watching.